In this lecture, we're going to continue our discussion of one-way ANOVA, particularly with respect to what is called the post hoc analysis. So to review our experimental situation, we examined the balance performance differences between 5 different groups of athletes. And what we had found is that there was a detectable statistical difference between the 5 different groups. So yes, the overall ANOVA results gave some confidence that we could reject the null hypothesis and consider the alternative as being plausible. And to review the descriptive data here, we have the number of balance falls, as we can see here, for the different groups of athletes with the mean and the standard deviation. But the question that we have here is that following the overall ANOVA test, which athletes are different from each other, or which group of athlete were considered statistically different from each other. And so what we see here is that we need to conduct more statistical testing, and this is called post hoc testing, and I'll define that here on the next couple of slides. And to do this, what we do need is the ANOVA table. So this was generated from the overall ANOVA test, where we had computed the sum of squares, degrees of freedom for the relevant variance terms, the actual 2 variances that were computed, the variance between the groups, the variance that existed within the groups, the test statistic, or the overall F value, and the associated probability of committing a type 1 error, or the so-called p-value. And what we found is through our calculations, the F value computed from the data was 7.99, or approximately 7.99. And we compared that with the critical F value for the associated degrees of freedoms at the nominal type 1 error rate of 5%, or the 95% confidence level. And that uh, critical value from the ANOVA table or from the statistical table was 2.69. So we rejected the null hypothesis, indicating that there is a difference between the different athletes, but we don't know exactly which group were different from which group. And so that's where the post hoc procedures are important. And I'll just post this up here for this table here at the bottom, but we first take a look at post hoc. And what post hoc basically means is that it occurs after the event. The main event is the ANOVA procedure. So what we had covered in part 1 is that the overall ANOVA procedure was considered a confirmatory test. So through that, we confirmed that either the null hypothesis or the alternative hypothesis was tenable. Which of those two are the most plausible situations given the data? And so the overall procedure for the ANOVA is often called the omnibus F test. Omnibus, which generally means overall. It doesn't distinguish inside which group is different from which group. So the post hoc procedure is actually an exploratory test. So once we've confirmed that the alternative hypothesis is the more plausible of the two, given the data that we have, then we venture into exploring where those differences exist. And that's performed after the ANOVA if the test statistic from the data, or the F obtained, is at least as large as the critical value. So what we're doing here is we're exploring where those differences existed between the groups. And the post hoc procedure is often referred to as the multiple comparison procedures because we're comparing one group against another group, and we do that a number of times. Now, in terms of post hoc procedures after completion of the analysis of variance, we see that there are at least 6 different ways to do this. And there are actually more, but I'm just posting these 6 here. And so we have what's called Fisher's least significant difference test, Duncan's multiple range test, Newman-Coules, Tukey, Bonferroni, and Chaffee. Now, what makes these different from each other is based upon the degree of whether we want to have a high standard for establishing a statistical difference between any two given groups, or we want to be a little bit more liberal in being able to determine if there is a statistical difference between any two groups. So, in this order, the ones closer to the top are more likely to find significant differences between paired comparisons of the different groups. So we would say that as we move from the bottom to the top, these statistical tests are considered to be more statistically liberal. That means that the standard for establishing a difference between any two groups is the lowest as we move from the bottom to the top. Stated otherwise, if we move from the top to the bottom in our selection of these different procedures, we become more conservative. So at the very high end of the of setting the highest standard for determining and stating which pair is statistically different, the Chaffee comparison is the most conservative, and so this is the one that would less where the comparisons are less likely to be significantly different. And in the subsequent videos, we're going to compare the Fisher's test against the Tukey test. The Tukey I have in bold because the Tukey post hoc procedure is the most common post hoc procedure that is performed following ANOVA. So this ends this first video on part 2 of our ANOVA review.